is going to be a more normal one, although I can't tell you what would be on the test, but this is going to be more equivalent to what you'll be doing most of the time when you do Thevenin equivalence in your everyday life. So we're supposed to find the Thevenin and Norton equivalent of the circuit. So if you found one, you found the other. They're just related by Ohm's law. So if you find one, you find the other. And so we're going to look at where we are told to find it. This one, it doesn't say specifically, but there's this one thing that's labeled RL. That would be the load resistor. That's what we're talking about. And so the one thing that we almost always are going to find, I can't think of when we wouldn't, is V open circuit. So we want to find the voltage across this open circuit here. And so I'm going to redraw it as an open circuit. Now, for the first part of this problem, when we're finding V open circuit, it doesn't matter that one of our resistors doesn't matter. This 20 ohm resistor on the top right doesn't matter because there's no current flowing through it. And so since there's no current flowing through it, it's not changing the voltage, there is no current, so we don't have to worry about it for finding the open circuit. We do have to worry about it for finding the Thevenin resistance, because it is definitely part of the resistance of the circuit on the other side of that resistor, but we don't have to worry about it for finding the open circuit. Okay, so now let's see. If I'm looking at this, let's say I will do nodal analysis. That's my favorite kind of analysis. So I'll call that V1 and V2, and I'll make this ground. And for nodal analysis, you write the sum of all the currents coming out of a node. And here is how you do it. So you take the sum of all the currents, sum of all the currents coming out of a node, and that equals 0. And a current coming out of a node can look at a couple different ways. You could have V node minus V at the other side of the resistor over the resistance. So for instance, if this is my node and I have a resistor going this way, so I'm doing nodal analysis on this node right here, so that's V1, and maybe that's V2, and that's V3, and this is ground, then, and this is R1, R2, R3, then my currents coming out of V1 would be V1 minus V2 over R1 plus V1 minus ground, which is 0, over R2 plus V1 minus V3 over R3. And that would equal 0. So that's one way that you can have the currents coming out of a node. Another way that you can have the currents coming out of the node is if the currents are explicitly given, like you have a current source. So a current coming into a node is negative, and going out is positive. So I'm now going to write my node equations for my two nodes here. So for V1, I have a current coming in. A current coming in is negative. So that'd be negative 1 amp. So that's So I'm looking at the current and going out in all directions. So I have -1. Plus, I made the bottom, oh, I didn't even have to make the bottom ground, it was made ground for me. But plus, and then going down, I'd have V1 minus 0/8. Plus, going across, I'll have V1 minus V2/10. And that equals 0. And now I'll do my node equation for V2. So, and y'all need to, like, I'm really bad with making arithmetic mistakes, so please, if you see me making one like y'all did on the last problem, please let me know. So V2, so now I'm doing for V2, and so I want all the currents coming out. There's only 2 of them. So V2 minus V1/10 plus V2 minus, now right on the other side of the resistor, the voltage is going to be 2, because at the bottom it's ground, that's 0, and then I have a voltage source, and the positive side is going to be 2 higher than the negative side, and it's 2 volts, and so it would be 2 right there. So this will be V2 minus 2/30 equals 0. So now that's not what I wanted to paste. Okay, so now I want to simplify these equations. So I'll multiply the top one through by 40. And the bottom one through by 30. So that gets me minus 40 plus 5V1 plus 10V1, plus 4V1 minus 4V2 equals 0. That's my top equation. So that would be 5V1 plus 4V1 is 9V1 minus 4V2 equals 40. And my bottom equation, I'll have 3V2 minus 3V1 plus V2 minus 2 equals 0. Or that gets me plus 4V2 minus 3V1 equals 2. So those are my 2 equations. So solving those, I get 6V1 equals 42, or V1 equals 7. And then I'll pick one of those, I'll pick the bottom one to plug into. -3 times 7 plus 4V2 equals 2. -21 plus 4V2 equals 2. 4V2 equals 23. Oh, I liked it when I got an even number there, but V2 equals 23/4. And let's see, does one of those happen to be, yes. So V2 would be in fact V-Thevenin, because V2 is the same all the way across this. So this is V2 and this is 0. So the difference between these two would be V open circuit or V-Thevenin. And V2 is whatever 23 divided by 4 is. So 23 divided by 4 is 5.75 volts. Did anybody see any mistake I made along the way before we go on? Nope? Okay. All right. So now it's time to find R Thevenin. So to find R Thevenin, we take our original circuit, and I disable, yes.
Can you explain that part at the top, the V2 to V0, and you said V open circuit is equivalent to V7?
Yes. So what we're trying to find is V open circuit. So we're trying to find the voltage between, the voltage difference between this point right here and this point right here. We labeled this point ground. We made this our well, it was actually labeled for us. So that we're calling 0. So this one right here, what the difference between this voltage and ground, V minus 0 is V. It's whatever this voltage is. And this voltage is the same all the way up here because at an open circuit there's no current flowing. And so V2 was our voltage at this node, which is the same as our voltage here, which is the same as V Thevenin. Did that answer the question?
Yeah, and then so voltage of an open circuit is always V Thevenin?
If it is the part where V open circuit is V Thevenin at the place that you're looking at. I mean, this would have a completely different Thevenin equivalent if I was looking at this resistor right here. Like you're told where to find it. But yes, the open circuit, V open circuit is V Thevenin, and that is. Remember how I said you're almost always going to find V open circuit, and I said I can't think of when you wouldn't find V open circuit. So the three ways of finding R Thevenin are external source, which sucks, which we just did a minute ago, that you have to do when you have a dependent source. There's also short circuit, I short circuit, V open circuit. I don't ever use that one. You can. It's the way I think he did it in the example on your test. But for me, I much prefer resistor simplification. I like resistor simplification, product over sum, those sorts of things. And so that's what I do. And so rather than finding the I short circuit, I do resistor simplification. And it works as long as you don't have any dependent sources. But what you do have to do is disable your power sources. And when you disable your power sources, current sources become open. And voltage sources become short. And now my job is to simplify the resistors to the left of where my terminals over here. So the only tricky part is deciding. You think it's easy to decide, and it suddenly gets harder to figure out if things are in parallel or in series, because you have to see how they are from the point of view of your Thevenin load that you have right here. So first of all, we see that this open circuit right here is irrelevant, and so really our circuit looks like this. And from this, it is easy to see that the 10 ohm resistor and 8 ohm resistor are in series. And so I can rewrite this as, now the way I'm going to draw it is going to make it obvious whether it's in parallel or in series with the 30. But I might not have drawn it that way. So I'm going to draw it like this when I combine them. I put my 10 ohm plus 8 ohm over here on this side so that it's really easy to see that these two are in parallel. But even if they weren't in parallel, you'd have to look and see relative to the resistance that we'd be looking at over here on our load. Are they in series? Are they in parallel? And they are, in fact, in parallel. And so the equivalent resistance of these two, 18 parallel with 30, is 18 times 30 over 18 plus 30. Which is 11.25. So now I have $11.25 and 20 ohms, and now I can add these together and I get 31.25 ohms is our Thevenin. So my Thevenin equivalent circuit has my voltage source. Can anyone remind me what we got for the voltage source? 5.75. So there's my Thevenin equivalent. My Norton equivalent looks like this. You have I Norton and R Norton. Well, R Norton is the same as R Thevenin. So we already have that. That's 31.25. And I Norton, we know that V equals IR. I equals V over R. So I Norton is 5.75 over 31.25. Is 0.184 amps. So that's my Norton equivalent circuit. Okay, questions on this? Any questions from y'all out in the world? Yes.
So if you go 5.75, you get that from B2? 20.
Yes.
How is B2 the same as the voltage source?
Wait, so the Norton equivalent is the same as the Thevenin equivalent, except it's like a source transformation?
Yes, exactly.
All right.
Yep. And then the question, I just had a question about V2. So I found V2 to be 5.75. And that was V open circuit, which is also V Thevenin. And so that is, so that's where that came from. Where did the 1 amp source go? Well, the 1 amp source went away because when you find R Thevenin, you get rid of all sources. And so not only did the 1 amp source go away, the 2 volt voltage source went away. So current sources go to open circuits. So that was this right here. Current sources go to open circuits. And voltage sources go to short circuits. So that's where the voltage source was. And that's what you do when you're finding the Thevenin resistance. You do the same thing when you find the Thevenin resistance, when you're finding the R, when you're finding in the time constants, when you're finding RC or L over R, that's the Thevenin resistance. And you you disable all of your power sources when you do that. Okay, other questions? All right, I'm going to stop this and say